Section 24 begins our look at exponential investigations. In the warm-up, we're asked to complete the table of values for three different functions. We have 2x, which we're going to call that y1. We have x squared, we're going to call that y2. And we have 2 to the x, which we're going to call y3. Now there's a reason I'm calling that y1, y2, and y3, because to fill out this table of values, I think probably the easiest thing for us to do is to put those into the graphing calculator. So I'll move over to our graphing calculator here. So in y1, so I'm going to go to y equals, and I'm going to clear those guys out since I don't need those. In y1, I'm going to type my first function, which was 2x. And it did something weird. Hold on, 2x. And then I'm going to hit enter. And for y2, I've got x squared. Hit enter. And for y3, I have 2 to the x. 2, and then the caret key, x. Now if I want the table of values, I'm going to go ahead and get to my table, which is at second graph. But I'm going to double check something first. I'm going to go to my table set to make sure it's good to go. So second window gets me there. Starts at -2. That's okay because I'm starting at -1. That seems to work. And my delta table, again, the successive values between each number is 1. That's what I'm looking for. So now that my table is good to go, I'm going to go to second and graph, and here's my table. So I've got my numbers here, -1, 0, 1, and 2. Those are the inputs that I'm looking for. So the first column in y1, that 2x, I can just copy these guys down. And I can do the same thing for y2 and for y3. So what I end up getting are these values here. Now, the interesting part about this is this has three different types of functions, kind of the main functions we're going to look at this year. The first type is a linear function, so it's y equals 2x. The second type is a quadratic function, x squared. And the third is an exponential expression. Now, this one right here is the one we're really focusing on. What makes it exponential is the fact that it has a variable in the exponent. So x squared is not an exponential expression. It's just a quadratic. This is because the variable is up in the exponent. And that's going to change the way things look a little bit when we start actually graphing these. All right, so our first activity dealt with scientific notation. So scientific notation is really helpful when you're dealing with very large numbers and very small numbers. So very large numbers, something like we could measure the distance from the Earth to Jupiter in feet. That would be an example of where scientific notation, a very large number, would be helpful. Instead of writing it out like this, trying to keep track of all those zeros, we can write it in scientific notation to make our math a little bit easier to work with. In addition to that, we can deal with very small numbers. So the wingspan of a gnat in terms of miles, that would be a very small number. That would have a negative exponent. Scientific notation is always built on three parts. One is the coefficient, and this is really a key idea that the coefficient has to be greater than or equal to 1 and also less than 10. It's got to be between those two numbers. If it's anything smaller than 1 or bigger than 10, it's not in proper scientific notation. The base is the part of the exponential expression, and it's always 10. We count in base 10, so base 10 is the easiest thing to do with scientific notation. And then we have an exponent, which tells us how many places we need to move the decimal point to make it in standard notation. So if I had a number like this, 5.2 times 10 to the 12, that means I have to move the decimal place 12 places over and fill zeros in wherever I've got those empty spaces. And that's what we have up here. If this was a negative 12, that would indicate I moved to the left. So starting here, I move to the left 12 spaces. And any place that I have an empty space, I just fill in zeros. So in this card sort activity, and I'll just kind of run through the scientific note, or the standard notation, the scientific part. We're trying to match the scientific notation and the standard notation. So in the first one here, we've got 1.23 and all these zeros here. So to write that in scientific notation, I've got to figure out, well, my decimal point is right here, and how many places would I have to move to put it between the 1 and the 2? So I'd have to move 1, 2, 3, 4, 5, 6, 7, 8, 9 spaces. So that number would be 1.23 times 10 to the 9th. Again, the decimal point's at the end if we don't see it. Similarly here, I could do the same thing. 1, 2, 3, 4, 5, 6. 1.23 times 10 to the 6th. Now, an interesting pattern about this, and it continues for all these with a large number, is if we have something like an exponent of 6, what that tells me is that normally I'm going to have 6 places following the decimal point if I'm turning it from scientific to standard. But in this case, we have these 2 and the 3 filled in. So because I've already taken care of those places with numbers, 0 is going to fill the rest of it. The same thing here, we had 9 places after the 1. So 2 places were taken up, 7 left over for those zeros. And again, it works the same for these as well. This one would be 1.23 times 10 to the 7. Yeah, 7, there we go. And this one down here would be 1.23 times 10 to the 10th. And 1.23 times 10 to the 5th. Then we get the negative exponents. It's the same basic idea, but working backwards. So if I move it this way, I've moved it 6 places. So it's 1.23 times 10 to the negative 6. And you may start recognizing a pattern here that I moved it 6 places. I got 1, 2, 3, 4, 5 zeros. The pattern continues if we take this number here. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1.23 times 10 to the negative 9 gives us 1, 2, 3, 4, 5, 6, 7, 8 zeros. So I can count the number of zeros and just kind of add 1 to find out my power. 1, 2, 3, 4. So that would be 1.23 times 10 to the negative 5. I see 1 0, so it would be 1.23 times 10 to the negative 2. I see 1, 2, 3, 4, 5, 6, 7. So 1.23 times 10 to the negative 8. And that pattern works anytime you have a very small number. And those are the answers for the scientific part. So then we have our closure. The closure is comparing numbers. We want to know which number is larger. So to evaluate these first two, we're just going to plug 4 in. So I take 2 times 4, which is going to give me 8. And then 2 to the 4th will give me 16. That's a bigger number, so 2 to the x will be bigger. And generally speaking, exponential functions will be larger than linear. The exception we get into is number 2, where we have that negative exponent. What that negative exponent does is bring that 3 to the x at the bottom. So this will become 1 over 3 to the 3rd, or 127. Here we'll have 9. 9 is definitely bigger than 1 over 27. And number 3 is kind of a tricky question because the gut instinct says 7.12 is bigger. However, the fact that this is an exponent of 7 and this is an exponent of 5 is really significant. What this is saying is that this has 2 more trailing zeros, which effectively it's about 100 times as big. Because if 1 0 is times 10, then another 0 is times 100. Not exactly, because 7.12 is a little bit bigger than 3.95, but it's in the general area. So this number is going to be a bigger, larger value. And down here on number 4, circle the larger value. Again, a negative exponent, a negative 3, 3 leading zeros. Where this one only, 2 leading zeros, because we take the 1 away. This one will only have 1 leading 0. We move the decimal 2 places over. So that will be a slightly bigger number, a power of 10 bigger, but a bigger number, but still relatively small.